Hello and good afternoon, CSI-158 Section 844 students for the second 8-week term in the fall 2014 semester. A number of students had asked for a supplemental OSPF tutorial to be done up in addition to the lecture that we did to cover not just some of the basic concepts that we went over, but to cover some of the key or the core concepts from Chapter 8, which was on OSPF, specifically the OSPF auto cost reference bandwidth, as well as the bandwidth command and the IP OSPF cost command. And so we're also going to take a look at the DR-BDR election on multi-access segments, and we're going to see why that does not take place in the OSPF point-to-point setup that we have here. So if you take a look, this is actually our topology. I have the iOS versions that are running. These are Cisco 1841, so ISR G1 routers. We've got a guy here that's R5 is 12.4 code, but R4 and R6 are running the 15.3 code. And the reason for that is we want to be able to take a look and see how the routing table entries are going to be a little bit different between the 12.x branch of code and the 15.x branch of code. All right, we have our subnet assignments here. As you can see, I just simply use the subnet as a 10 dot and then the lower router to the higher router for the second and third octets. Same thing here on the serial link, as well as this link here. And then the individual IP interface, or the individual interface IP, will simply be the router number. So router 4 on this link will be .4 and .4 here. We've got some loopback addresses that we're basically just going to use to simulate networks that sit behind router 4, router 6, and router 5 when we go to take a look at the cost. And let's go ahead and jump right in. As you can see, we're at the default configuration here. So on router 4, I'm going to say no. Router 5 will say no. And router 6 will say no. And so we'll come back over here to router 4. We're going to, excuse me, I'm going to operate on configuring router 4 right out of the gate here. So we're going to go from privilege exec into, from user exec into privilege exec, and then we're going to go into global config. And the first thing that we want to do is we'll go ahead and set the router host name. So even though it says it up in the tab, I want to make sure that when we're looking here at the command line, we know which router we're actually configuring. Okay, so we've got the host name entered in, and I'm going to go ahead and actually turn on debug IP OSPF adjacency, and we're going to do debug IP OSPF hello. And the reason is we want to take a look at the different packets that get sent, and we want to capture the adjacency information, and we want to see how those hello packets get sent, received, and processed. All right, so on router 4, we're going to do very similar to yesterday. So I'm going to go ahead and jump right in. So we're going to do router OSPF, and the next value is going to be the process ID. Now the key to remember here with the OSPF process ID is that the process ID is locally significant. So I'm actually going to use a different process ID on each of these 3 routers. Keeping in mind that when you go to work with EIGRP, it's the exact opposite. With EIGRP, remember it's an autonomous system number, right? And as you can see, I've got the this version of code has the new EIGRP named setup, but we're not going to be doing that. We're worried about the autonomous system number here. So the autonomous system number with EIGRP, those have to match. If those don't match, then you will not form an adjacency. So just remember that. The OSPF process ID is locally significant, so I could set this to 4 on router 4, 5 on router 5, and 6 on router 6, which is actually what we're going to be doing here. So we'll say router OSPF 4. Now when I hit enter, we should see a message of some kind, and there it is. So we've got an error message here. It says OSPF no router ID, right? And so that's what this message is telling us. So process 4 failed to allocate a unique router ID and cannot start. So if I were to do a do show run, OSPF show, not show run, do show IP OSPF database, you can see that the process is not running. It says please configure a router ID. So the way that the router ID is selected, if you remember back from the reading in chapter 8, the router ID, the first priority would be if the router ID is set. So if I set the router ID here, and again it's a 32-bit ID that is in IP address format. So we're just going to say 4.4.4.4. And so if this is set, if you have the router ID set, then this is what OSPF is going to set the router ID to. Okay, so this takes precedence over the other options that OSPF will look to process in order to set the router ID. And so here the router ID is just simply 4.4.4.4. Now, also remember that this is a router ID, and even though it's an IP address format, it is not an IP address. So I can't ping this router ID, I can't redistribute this router ID or advertise this router ID as an IP address. It's just simply the router ID. Now, if I had a loopback address, and I'll come up here on router 4, so let's say that in addition to these loopback addresses, if there was a loopback address 4.4.4.4, then that would be different, right? Because that would be the loopback address. So then I could advertise 4444, or I could redistribute it, or use, you could ping that IP address if it was reachable. And so that's the difference. And remember that the router ID, even though it shows up in IPv4 format, is not an IP address. Also, with IPv6, the router ID stays the same, right? It is still a 32-bit value that is depicted as an IPv4 address. So even with IPv6 or OSPFv3, your router ID is still going to be a 32-bit value that's represented as an IP. All right, so let me go ahead and I think it's Control-Z, pull these out of here, clean that up. Okay, so we've got the router ID set right now. So if I were to do a do show IP OSPF database, you can see now we receive something different back from OSPF. In fact, it's now telling us OSPF router with ID 4.4.4.4, process ID is 4. So we actually have the OSPF process established here on router 4. However, we have not configured any of the interfaces on router 4, and we haven't started the OSPF process on any of the interfaces. And so let's go ahead and do that. So we're going to jump into interface. Let's do FA00 first. I'll say no shut, and we're going to say IP address 10.46.46.4, and it's a /24, so 255.255.255.0. So if I do a show IP interface brief, you can now see that Fast Ethernet 00 has an IP address assigned. It's up, however, the layer 1 is up, but layer 2 is down, so we don't have a connection on the other side, so we'll have to get over to router 6 to fix that. But right now we're going to go into serial 010, and we're going to do the same thing. We're going to say no shut, and we're going to say IP address 10.45.45.4, and again it's a /24. And so we've applied that. So again, if I do the do show IP interface brief, we should see we have 2 interfaces configured and ready to go. So now, if we want both of those interfaces to actually run the OSPF process, we need to tell OSPF that that's what we want. So we're going to go back into the OSPF router config for process ID 4, and here's where we add the network statements. So I would say network 10.46.46.0, and what's key here is that this is not a subnet mask. So we're going to use a wildcard mask here. And let me pull this down just a little bit to get up here. So for a wildcard mask, remember that when you are dealing with the wildcards, and so we'll say wildcard masks. And I'm going to make a statement here, just like I did in class, that 99% of the time at the CCNA level, the statement that the wildcard mask is the inverse of the subnet mask, that's a true statement. However, when you advance on, keep in mind that that's not always the case. But we're going to reserve discussion on those instances for Chapter 9, and I'm going to be doing a supplemental access control list video as well. So what do we mean it's the inverse? So here we've got a /24, and we know that a /24 is 255.255 in dotted decimal notation, .255.0, right? So we have 8 bits here, 8 bits here, 8 bits here, and no bit values are on there. So that's where we get our 24, is 8 plus 8 plus 8, right? And we can even say plus 0 equals 24. So in order to determine the wildcard mask, what I want to do is I want to take all 255s, 255.255.255.255, and this is sort of our baseline for the wildcard mask, and we're going to subtract what our current subnet mask is. So 255.255.255.0, and this will give us the inverse, 0.0.0.255. And so this is our wildcard mask for a /24. So let's take a look at another example here. So if we had a /25 as the subnet mask, which would be 255.255.255.128. So what we would do is, again, put down, let's go back up one here. So 255, so the all 255s, which is our baseline for wildcard masks in this calculation. So that's the baseline. And we're going to simply subtract 255, our current 255.255.128. And when we do that, very simple math, 0.0.0.127. And so this would be the wildcard mask if we were using a /25. Okay, so that's how we calculate the wildcard mask. Again, here it's very straightforward. We're using /24s, and so our wildcard mask will be 0.0.0.255. So let's go ahead and drop that in here. So we'll say 0.0.0.255. Now, we're not done. So if we do the question mark, you can see that we have a choice here. We have to set the OSPF area ID. And so remember from our conversation in class, talking about single area OSPF versus multi-area OSPF. So if I have router 1 and router 2 and router 3, right, and these routers are connected together, very similar to what we have over there, and this is going to be my OSPF area. The best practice is you want to go ahead and you want to use area 0, right? We want to make it 0. Now, do you have to? You certainly don't. If you know for certain that your OSPF area is never going to grow or incorporate another area, let's say I added in a router here, right, and this would be my area border router, and if this was R4, so he's connected here, and then I've got another area out here, right? As soon as we do this, okay, and let's say this is area, well, we'll use the book, area 51, right? So we'll say this is area 51. So if this was area 51 out here, and I did not start my OSPF with area 0, this would not work, right? So the type 3 LSAs would not make their way through. So if this was area 10, and I figured when I set this up initially, I'm never going to get, my environment will never grow any larger than it is, so I'm just going to use area 10 because 10 is my favorite number. And then, for whatever reason, I have to add in an area border router, and I've got to configure another area, and I want these areas to interact. It's not going to work. And so that's why the best practice is always use area 0. And when you're starting out with your network design and setup, you should always use area 0, even though, you know, you can use 51 if you want, you could use 10, you could use just about any number you want. However, if you go to incorporate additional areas into your setup and you do not have the backbone area, area 0, those additional areas are not going to function properly with what you did configure as your backbone area if it was not area 0. So again, make sure always, right, and I'm going to go ahead and say always, even though you can use any number you want to, but always make sure you use area, area, let me back that up there, I was going to do 0. Actually, we'll pull the eraser out here. So always make sure that you use area 0, right, for your OSPF area when you're starting out. And then when you go to add on, if you're tacking on different areas, then you can pick and be creative with the area numbers you want. However, make sure it's area 0. I can't stress that enough. All right. So our area is simply going to be area 0. If I do the question mark, you can see that you can certainly choose from some pretty large area numbers. The value can be a decimal, and it can also be a 32-bit IPv4 address format, right? So I could do, you know, 192.168.30.45, okay? However, we just want to go with area 0 here. All right, so I'm going to put this interface, 10.46.46.0 on router R4 into area 0. And now we're debugging the hello packets, and so let's see what happens here. So I hit enter, and as we would expect, we should see here in a couple seconds, and I'm pretty sure we're debugging the hello packets. We don't have anybody up on the other side, so we'll come back to the hello packets going out. So we've set up OSPF to run on that interface. So if I do a do show IP OSPF database, you can see now that we have the link ID, and this is a type 1 LSA. This is the router LSA. So you can see we have the link ID, which is the router ID. We've got the advertising router, which is also my router ID. 25 seconds is the age. We have the sequence number, and it starts out at this number, right, with 1. And as we start to have changes in the OSPF area, this number will increment. We have a checksum that checks the validity of the updates, and then we also have the link count, right? So right now the link count is at 0. I've got nobody on the other end of my link. Okay, so we also want to set up OSPF to run on the interface serial 010. So the network statement will be this very similar, 10.45.45.0. Again, wildcard mask, not the subnet mask, and we're going to put him in area 0. All right, so we've started up OSPF on both interfaces on router 4. You can see that that's the only router that router 4 sees, because that's the only router we've configured at this point. In addition to that, you can see that the router ID is 4.4.4.4 and the process ID is process ID 4. So let's go over to router 6 now. So the first thing we want to do is go from user exec to privilege exec. We're going to go into global config, and I want to get the host name configured. That way when I'm bouncing back and forth between the routers, I know which one I'm configuring. And now we're going to go ahead and turn on do debug IP OSPF adjacency and do debug IP OSPF hello, because we want to see the hello packets. And in fact, you can actually debug IP OSPF. If you take a look here, there's quite a few things with OSPF that you can get debug information on. I also like to debug the events as well, so we'll go ahead and on router 6 we'll do a debug on the events, because we get to see a lot of very valuable information that the routers generate with respect to the OSPF conversations that they're having between each other. Okay, So on router 6, we're going to go into router OSPF, and we're going to use process ID 6. And so the adjacency will establish even though we're using a different process ID, because with OSPF, the process ID is locally significant. So as you would expect, we get our no router ID because we haven't set the router ID yet. And we don't have another interface configured. So to continue that conversation, if the router ID is set, like we're setting it right here, and we would set it to 6.6.6.6, and I'll make sure I remember to do this on router 5 so you can see what happens. When I set it here, this is going to be the router ID, right? Now, if the router ID is not set, then the router will look to the highest numbered loopback address, right? It'll look for a loopback address, and it's going to pick the highest numbered loopback address. Now, what do I mean by highest numbered loopback address? On router 5, we're going to set this up. You can see we've got some loopbacks, so I will set these up before we turn on OSPF, and then you can see what will happen. So, and by highest numbered, I don't mean loopback 1 is less than loopback 99. It's specifically looking at the IP address of the loopback address. All right, so the first decision that OSPF will make is the router ID configured with the router ID statement right here under the OSPF process ID? Is this configured? If it is, then this becomes your router ID. If this is not configured, then OSPF will select the highest IP loopback address. If there are no loopback addresses configured, the third and final fallback is that OSPF will grab the IP, the highest numbered IP address off any interface that is not in a down state. And remember that down is different than administratively down and down. If there are no IPs, like in our case here, I mean, this is a brand new router. If I were to do show IP interface brief, you can see we've got 3 interfaces. They're all down. We have no IPs assigned. There's no loopbacks assigned. So we've got nothing. If those 3 checks all fail, in other words, there's no router ID, there's no loopbacks configured, no loopback addresses configured, and no interfaces are configured with an IP, and they're not in the down state, then we get this error message right here telling us that no router ID, the OSPF process failed. And so now let's go ahead and jump back in. So router ID 6.6.6.6, and at this point the router ID is configured, and we see we get an OSPF event message from our debugs. All right, so with the router ID configured, let's go ahead and configure the interfaces. So we'll go into int fa01, and we're going to say no shut, and IP address 10.46.46.6, and I'm going to put the subnet mask in there as a /24, and as you can see, we've added an address, and so we're picking up some OSPF events, right? Address removed, topology state change, address changed, route adjust. So it picked up the fact that we've brought the interface up and that we have added an IP address onto the FA01 interface. If I do a do show IP OSPF database at this point, I don't have any information yet. I know the process is running on the router. You can see it here because it recognizes that the router ID is 6666, and it also knows that the process ID we used is process ID 6. However, we now have to tell the router to start the OSPF process on the FA01 interface. So before we do that, if I do a do show IP route, you remember that router 6 is running the 15.x branch of code. So we're going to see a connected entry as well as a local entry, right? And the local entry is simply reflective of the interface on with the IP on the interface that we've configured on this directly connected subnet here. So we have entries here already, and again, haven't even added this interface that's in this subnet into the OSPF configuration, and these interfaces are here. In fact, let's check. Can I ping router 4? And again, OSPF is not running on router 6. And so this is to show you that you don't have to have OSPF running in order to establish the connectivity between the routers. So 10.46.46.4. And so the first failure is because it had to ARP out to find out the neighbor, to learn about the neighbor. And so now you can see we have connectivity, but we don't have OSPF running. Because again, do show IP route, this is directly connected. And if I come back over here to router 4, aha, and as soon as the interface came up, we've got some great information here on router 4. You can see that the interface came up here, and now on router 4, we're in the wait state. Because the OSPF process is running over here, right, on router 4, and so he's trying to establish an OSPF adjacency with router 6. So he's in the wait state. So he's just sitting here waiting, and you can see that right before the wait state happened, we had a hello packet. And remember, the hello packets get sent out to the multicast address 224.0.0.5, and inside that hello packet there are specific bits of information. One of those pieces of information is the IP address of the router that's sending the hello packet. And the other is going to be, as we're going to see, the subnet mask is also being sent. So the interface state changed to up, new OSPF state is wait. So right now router 4 is waiting. He's waiting for router 6 to reciprocate and begin to send the hello packet so that the adjacency can be established. In fact, he end of wait on the interface here. And since this is a broadcast network that we have here, it is not point-to-point, the DR-BDR election took place. And router 4 took a look, and again, remember that the BDR is elected first. So he elected himself as the BDR, then he saw that no one else was the DR, so then he unelects himself as the BDR and then elects himself as the DR. And again, DR is designated router, BDR is backup designated router. We're going to talk a little bit more about that in a second here. And so as you can see, we have a DR of 4.4.4.4, but no BDR. And the hello packets are going about every 10 seconds. You can see we go all the way to the milliseconds here in our log messages. So that one was 10 seconds. You can see this one was 9, but it was just off by a few milliseconds. So every 10 seconds, we're going to have this information being sent out. If I do a do show IP OSPF interface on FA00, this is where we can come in and take a look and see what are the timer intervals and how are those configured. So the hello interval is 10, so 10 seconds. And our dead interval is 4 times the hello interval for a broadcast type network. And so it's set to 40 seconds. And so it's after 40 seconds, if hellos are not received, that the relationship, the adjacency is declared dead and will then be torn down. And so we're debugging the hellos, so this is working great. So let's come back over here to router 6, and let's do the same thing that we did on router 4. So we're going to go router OSPF 6, that's our process ID for OSPF on this router, and now we're going to add in these 2 network statements for router 6's networks. We're going to say 10.46.46.0, 0.0.0.255, and we're going to put him in area 0. And now what we should see here on both router 1 and router 6 is a lot of activity that's going to take place with respect to the relationship between the adjacency between router 4 and router 6. You can see here that the DR-BDR election has taken place, and router 6 noticed that router 4 is already the DR. And so we'll look at the priorities and how the DR-BDR election takes place here in a second. But you can see that database descriptors from router 4 have been sent and received, right? So router 6 has router 6 has sent and received database descriptors from router 4. The hello packets are now going to be sent, again, every 10 seconds because it's going to maintain the relationship. And you can see that it's receiving hellos and sending hellos, right? So we've got link state updates that were received. We have link state requests that were sent. So router 6 was sending a link state request to router 4, and it received a link state update from router 4 that updated router 6 with router 4's link information, right? And then we've gone from loading to full. So the state machine was in the wait state, and then obviously that expired while we were talking about the configuration. And then once it was configured on the router 6 side, the state machine went ahead and went through its process and brought it from loading to full. So if I do a do show IP OSPF database now, you can see that we have a type 1 LSA here, the router link state LSA. We also have type 2 LSAs. And remember, the type 2 LSA is only generated when you have a DR, okay? So on a multi-access segment, and we're on a broadcast segment, the type of OSPF network here is broadcast, which is multi-access. So we will have a DR-BDR election, and we will also have type 2 LSAs. What we'll see over here between router 4 and router 5 is this is a point-to-point network, right? And not only is it point-to-point, but we will not have a DR-BDR election, and there will be no type 2 LSA involved over here. Okay, so on router 6, what I want to do now is I'm going to go ahead and configure the loopback interfaces. So we're going to say loopback interface 10, which is going to be IP address 6.6.10.6. Whoops, we're going to get the subnet mask in there, 255.255.255.0. And then we're going to go interface loopback 11 and IP address 6.6.11.6. Whoops. Oh, I can't see there. I have to redraw it. So let me do a do you all. So do you all. I'm going to turn all debugging off here. So interface loopback 11, IP address 6.6.11.6. And we'll get our subnet mask in there. Get these three guys entered in. And then interface loopback 12. IP address 6.6.12.6. And again, we got the subnet mask 255.0. Oh, left off the address part there. Give me a second. All right. So I'm also going to advertise these out, right? We're going to originate these routes into OSPF. So as you can see, the hello packets are going back and forth. So let's turn this off here real quick. Turn all debugging off. So if I do a show IP route now, you can see that on router 4, I still see the directly connected network. And on router 6, we should see something very similar, right? So he's got the directly connected network, which is down here, the 10.0, and we're subnetted out here to 10.46.46. So he sees that network. We've just added in these loopback addresses. So those are shown as directly connected, right? Loopback 10, 11, and 12. And it also gets a directly connected to represent the subnet. And then it also gets the local entry, right, in the routing table on the 15.x branch of code. So now we're going to go ahead and we're going to originate these. We're going to advertise these in OSPF. So if I'm on router 4 right now, and I try to do a ping over to 6.6.10.6, is it going to work? And it's not, and it shouldn't, because router 4 has no route in its route table to tell it how to get over to that network. And so if I do a do show IP route on 6.6.10.6, you can see it says network not in table. All right, so let's change that. So now that we've got a dynamic routing protocol, OSPF running between router 4 and router 6, I'm going to originate these routes, so OSPF 6, and I'm going to just add in network statements. So we're going to say network 6.6.10.0, and again, we're going to put that in area 0. I'm going to say the same thing for 6.6.11.0, and I'm going to say the same thing for 12.0. All right, so if I do a do show IP route now on router 6, we see the same thing. Because again, these networks here that I'm advertising, these loopback addresses that I'm advertising, these are not being learned from someone else. These are local to router 6. However, OSPF is now running between router 4 and router 6. On router 6, we just advertised those loopback networks out. Now let's do a show IP route on router 4. And sure enough, OSPF is working, right? And so let's talk about these entries that are here. So the first thing that we want to focus on is over here in the first column, the O. And what that signifies is that this route has been learned, and if you look right up here, it's been learned from OSPF, right? Here is the network we've learned about, and this is specifically the IP address. It's 6.6.10.6. And so that's the destination network. And then we have next the administrative distance of OSPF, which is 110. The next and most important thing that we've got here on this line that we'll be talking more about today is the cost, right, or the metric. And this identifies the value or the cost to reach this network. And this is how OSPF determines which routes get added into the routing table. It goes and calculates using Dijkstra's algorithm, looking at the shortest path first to determine which of the routes has the lowest cost. Now, if we were running EIGRP and OSPF, and we had routes we had an EIGRP route to this network here and an OSPF route to that network, and the router would then fall back with all things being equal, because the metrics between OSPF and EIGRP, right, they're not apples to apples. They're figured out and they're calculated very differently, and the values that are used to calculate what this metric cost actually comes out to here are very, very different. So we need a tiebreaker, and that's your administrative distance. So if we had on router 4, if we had learned a route in EIGRP as well as OSPF, the EIGRP route would be installed into the routing table because its administrative distance is 90. So it's lower. So lower administrative distance, right? When you have multiple routing protocols, the lower administrative distance is preferred. However, when we're just running OSPF, it's going to be the lowest cost that's preferred. So what if the cost is the same? And we'll see that once we get router 5 online here and we start to talk about this network here, because from router 6's perspective, to get to this network, he has a 100 meg link here and a 100 meg link here. So he has 2 equal cost paths to get to this destination. And so we'll see that shortly. So again, inside the brackets here, we have our administrative distance for OSPF and we have our cost. What is it going to cost us to go from router 4 over the link here, the link between router 4 and router 6? That cost is going to be what? We'll talk about the auto cost reference bandwidth here, but since it's a 100 meg link, the cost is 1, and then we have a cost of 1 to jump to the loopback interface. Even though it's local on this router, we still have a cost of 1. So if I did a do show IP OSPF interface on FA00, we're going to see the cost, right? So the cost is 1 on this link. And remember, it's the cost of the link. It is not the cost of this interface plus this interface, right? It's the cost of the link. And so the link cost is 1. So if I do a do show IP route now for 6.6.10.0, whoops, 6.6.10.6, because that's a network in the table, you can see now we get some information on that. So we see that it's known via the OSPF process 4. That's how we learned about it on this router. The distance is your administrative distance. And then here's our metric. So again, it's our cost. And this is intra area because it's in the same area. It's in area 0. And again, we have our next hop IP here. So now that I know the next hop IP, I can total the cost up. So you can see here that the cost is 1. If that's my next hop, I could actually go ahead and do show IP route on that 10.46.46.6, right? And you can see here that the distance is 0, the metric is 0. It shows that it's connected, right? So it gives us some additional information. But now that I know where this network resides, right? It's over here on router 6. I can then come over to router 6 and run the same set of commands, which we'll do here in a second. So again, I take a look at the interface I'm going to have to go out. My cost is 1, right? And then over here on router 6, if I do the do show IP OSPF interface on loopback, and that's going to be 10, right? You can see that my cost is 1, right? So the cost for me to get across this link is 1, and then once I'm here, my cost to get to the loopback interface is 1, and that's where on router 4, when we looked at the routing table, do show IP route, that's how this number is being calculated. All right, so the next thing is the next hop IP, right? So this signifies the next hop IP address, and we know that this is over on router 6. Then you've got what's called the route timestamp, right? And so the route timestamp is simply the last time I had heard about this route was 6 minutes and about 30 seconds ago. And that'll continue to increment, right? And then finally, we've got the outgoing interface, right? So which interface do I need to go out to get to this next hop? And it's fast Ethernet 0, 0. And you definitely know that that's the exit interface, because the next hop interface, right, or this interface that we would go to on the other side, is FA01. So this is definitely the exit interface. All right, so let's go ahead and jump on to router 5. And router 5's got nothing, so we're going to go from user exec to privilege exec into global config. We're going to set our host name to R5. And we're going to go ahead and we're going to configure the serial link first. So let's say we do, or actually I want to make sure, we wanted to see what it looks like. So no router ID is configured. I'm going to go ahead and do the loopback interfaces first. So we're going to say loopback 10 IP address is 5.5.10.5. And did I leave out the address again? I sure did. All right, IP address. Okay, and then we're going to go ahead and set interface loopback 11, IP address 5.5.11.5. And then we're going to go ahead and set the interface loopback 12 to 5.5.12.5. Now we want to make sure, I'll leave address off again. PADDR. So we want to make sure, interface brief, that we've got our loopback interfaces are here. They're properly configured, right? So we've got loopback 10, 11, and 12. So now this is going to have the highest IP address. So what I'm going to do is we're going to put in interface loopback 99, and I'm going to make loopback 99 IP address 1.1.1.1. And we'll do that do show IP interface brief again. And the reason I'm doing this, we're going to remove it as soon as we're done. But what we want to make sure we see is the selection process for the router ID. Now this loopback number is higher than the rest. That is not how OSPF is going to pick a loopback address to represent the router ID. It's going to pick the highest IP address, and what we've got here is 5.5.12.5 should be our highest IP. So let's see if that holds. So now that those loopbacks are configured, the router ID is not configured. So I'm going to say router OSPF, and we're going to use process ID 5. When I hit enter here, we should not see the error message that we saw previously on routers 4 and 6. Because remember, those error messages telling us that there's no router ID configured are because we had no router ID statement under the OSPF router config. We had no loopback addresses configured, and in addition to that, we had no interfaces, physical interfaces configured with anything. And so as a result, we got that error message. So I'm going to hit enter here. And remember, on this router, we're using iOS 12.4.24T8. So there it is. We have no error message. So let's do show IP OSPF database, and let's see what our router ID is. All right, fantastic. As you would expect, and as we talked about, it doesn't pick the highest, and sometimes the wording in the text is a little confusing. When it says the highest numbered loopback address, it's not talking about the number on the loopback address, right? It's talking about the IP address that the loopback address is configured with. And we just proved that, because if it was the highest loopback number, right, it should have picked 99, but it didn't. It picked 5.5.12.5, which was loopback 12, but that is the highest configured loopback IP address that we have. Okay, however, we don't want to use that loopback IP address, so watch what happens. I'm going to set my router ID now, and let's see if the router ID statement that we just set actually overrides that loopback that got selected. And it does. As you can see, my router ID is now 5.5.5.5. Okay, so let's configure interface serial 010. All right, so we're going to go into interface serial 010. We're going to do a no shut, and I'm going to say IP address is going to be 10.45.45.5, and it's /24 to keep things simple. All right, so now that interface is up and running. If I do a do show IP route, what do we see? All right. Oh, let me get rid of, let me go out, let me make sure I get rid of that interface. So no loopback 99. No interface, sorry, no interface loopback 99. Yeah, we don't want that interface in there. Excuse me. So do show IP route. All right. So we have our 3 directly connected loopback interfaces, and we have the network 10.45.45.0. And what are we missing here? What do you notice is different with the 12.4 branch of code? We have the directly connected entries in the routing table. However, the 12.x branch of code does not show us the local entries, right? And so that's a significant difference between 15.x and 12.x code. All right, so my interface is configured. Can I ping the other side, which would be 10.45.45.4? All right, so we've got connectivity. However, do show IP OSPF neighbor, I don't see anything, right? If I come over here to router 4 and run that same command, do show IP OSPF neighbor, right? I see a neighbor. We've got the neighbor ID, which is the router ID identifying this neighbor. So from router 4's perspective, he sees router 6 as a neighbor. The default priority, right, for a broadcast network is 1, and the priority has to do with the DR and the BDR election. So by default, the value is 1. A higher default, or I shouldn't say a higher default, a higher value in the priority provides preference, right, or indicates that you want that router to be the DR, right? So if I set this to 100, what I'm saying is I want router 6 to be the DR. Now, if you set it to 255, or I'm sorry, if you set it to 0, as we're going to see here in a second on the point-to-point network, it's got a totally different meaning, and it's a different default in point-to-point networks. So my state is full, and router 6 is the BDR because I am the DR. The dead time, and you should never see that go below, right? As I'm running the command, it will never or should never drop below 30 seconds, right? Because there you go, right? So what you would anticipate to see, remember the dead time, this is 4 times, And let me pull up the pin here. So the dead time, right? Remember the dead time, that's 4 times, and boy, that is definitely much thicker than I wanted it to be. Let's make a quick adjustment here. Let's drop this guy all the way down. So the dead time, remember that is 4 times, right, the hello interval. So if my hello interval is every 10 seconds, that value should never drop below 30, or it may hit 29 and then fire back up, you know, for just a little time skew. But again, I should see my dead time, right, should be 30 seconds or greater or higher, right? So here we've got 39. It hit 30, but then what happened? It went from 30 to 39. Well, in between me running these commands, a hello showed up. And so when a hello shows up, it sets it back to 4 times the hello interval. So it dropped it to 39, or it incremented it back up to 40, and then it dropped 1 second to 39. So it's counting down to 37, and then when it gets down to 30 again, we should see another hello packet. All right, so let me clean that up. Okay, so where do we leave off here? So we're on router 4. We're taking a look at the show IP OSPF neighbor because 4 can see 6. However, on 5, he doesn't see anybody. And the reason for this is because router 5 has not been set up for OSPF to run on any of its interfaces. So let's do that now. Let's go ahead and set OSPF up to run on the serial 010 interface. And what we're going to do over here on router 4 is we're going to debug IP OSPF adjacencies. We're going to debug IP OSPF hellos, because we're going to see some different behavior here. And then we're going to debug, we're going to debug IP OSPF events, right? Gives us a lot of great information. So we'll jump back to router 5, and now let's jump into serial 010. Oh, I'm sorry. Go back to our router OSPF 5. OSPF 5. We've already done the interface. Do show IP interface brief. Have we configured that serial interface? We have, and it's in an up and up state. We've got connectivity between the two, but now we want them to speak OSPF to each other. So I'm going to go ahead and say network 10.45.45.0, 0.0.0.255, and then area 0, right? Because again, we want everybody in area 0 for this lab. All right, so as soon as I hit enter here, you can see that we have an OSPF adjacency change message, process 5, neighbor 4444 on serial 001, went from loading to full. The loading is done. So if I do a do show IP OSPF neighbor, we have a neighbor here. However, what is very different between the neighbor relationship between 4 and 5 and the neighbor relationship between 4 and 6? Our priority. So the priority of 0 is the default priority, do show IP OSPF interface on serial 010. So let's take a look here. So the network type is point to point, and this is very different from the network type between 4 and 6. And actually I'll jump on to 6. We want to go back and look at those messages there. So I'll come over to 6 here, and if I do a show IP OSPF interface on FA01, that is a network type of broadcast because it's an Ethernet interface, and Ethernet by default is a broadcast medium. However, router 5 sees the serial interface as point-to-point because by default the serial interfaces are not broadcast. They are point-to-point. You can also see that the cost is 64 for that link, whereas here on a 100 meg segment the cost is 1, right? So the default priority for a point-to-point network, right, is going to be 0 because there is no DR, BDR election that takes place, right? It's not needed because it's point-to-point. There aren't multiple routers that are on this link talking to each other. There are simply these two guys right here. So we don't need to elect a DR or a BDR. Again, remember the DR-BDR election is so that we have a single node in the topology, the DR, who's responsible for the generation and the sending of the link state advertisements, and that all of the other routers in that multi-access segment, they become adjacent to the DR and the BDR. They do not become adjacent with each other, right? Because from a scaling perspective, if you had 60 routers, you would not want to have each router having to form an adjacency with 59 different neighbors and then flooding its LSAs out to all of those neighbors. And so that's really the role of the designated router. He is designated to flood the LSAs out throughout the area when changes are taking effect or when changes have happened. And so you have a centralized control point with that DR. The BDR's role is simply as you would expect. He's the backup, right? So he waits for that DR to fail, and if the DR fails, then the BDR will take over as the DR. And we'll see that here. I'll go ahead and I'll reload router 4, who's our current DR, and you'll see that 6 will take over as the DR. All right. So on the serial interface, the default priority for point-to-point is 0 because, again, there is no DR, BDR election that takes place on point-to-point network types. Okay. So now if I do a do show IP route, let's see what router 5 has learned. So as you would expect, right, router 5 has learned about the 3 loopback addresses that we've advertised out from router 6. Now this link right here is not up. We have not configured this link between router 5 and router 6. So right now, router 5 is learning about the router 6 loopbacks via router 4 out his serial 010 interface, right? So that's how he's learning about them. And you'll notice that the cost is 66. And so let's talk about that again. The administrative distance for OSPF is 110, but it's the route with the best cost. Again, we're only doing OSPF. The best cost is going to be inserted into the routing table. So when we bring this link up here, what we're going to see is that this is no longer the best cost to get to these networks. So how do we come up with this here? This cost of 66. So if I do a do show IP route over to 6.6.10.6, whoops, to 10.6, let's see what it says here. It says that the distance is 110, the administrative distance, because we learned it from OSPF. The metric is 66. So what's my next hop? So my next hop is 10.45.45.4. And that's via serial 010. So if I do a do show IP route over to 10.45.45.4, we should see that it's directly connected, and I would go out serial 010 to get there. So if I know that I go out serial 010 to get there, I can calculate my cost to get there. So let's do a do show. We did this just a second ago. Do show IP OSPF interface serial 01. Oops. Serial 010. All right. So here it is, and there is the cost to jump over to that next hop, right? So the next hop is 10.45.45.4 for router 4. It's the IP address here. So what's the cost? So I have to figure out, if I know the next hop IP, I need to know the interface I'm going out, right? Because if my next hop is out this fast Ethernet interface, the cost would be significantly different. So that's when I do the show IP route. So tell me, routing table, tell me if I want to go to the next hop of 10.45.45.4, what's the directly connected interface? What interface am I going to be going out to get there? So it's serial 010. So that's when I do the show IP OSPF interface serial 010. So my cost is 64. So let's annotate that on our drawing here. So my cost for router 5 to go this way to get to 6.6.10.6, my cost is 64, right? So the cost for this link is 64. Now, we know we would end up over on router 4 after we make that hop to that next link. So let's come over on router 4. And as you can see, we've got a lot of hellos going here. And I'm going to do a quick U all. So undebug all, because I want to scroll back up here a little bit. And the hellos are going crazy there. So again, some of the adjacency debugging messages that we're seeing, right? And you can see this is the debug from the adjacencies, right? And this is the debug from the hellos. So database descriptors get sent back and forth. The neighbor negotiation takes place. And it goes from the exchange completes, and then your OSPF state, the state machine goes from loading to full, right? So the adjacency has been established. All right, so let's jump back over here. We want to see some other activity here. So now that I know the cost of that link is 64, what's the show IP route 6.6.10.6? So how is router 4 going to get to that network? So as you can see here, router 4 knows about that network. He also learned it from OSPF, administrative distance 110, and his metric to get there is 2. Now we've got the next hop IP. Now that I know the next hop IP, I want the routing table. So routing table, tell me out which interface, right, am I going to go to get to that network, because I need the cost for that hop. So it says it's directly connected via fast Ethernet 00. So that's where I would say, now I ask the routing table, now that I'm on router 4, how would I get from here, from router 4, over to that route, to that network? Where do I have to go next? It tells me that my next hop IP is 10.46.46.6. So now that I know the next hop IP, I need to know the physical interface out which I'm going to go, because that's how I'm going to determine my OSPF cost. So then I ask the routing table, I say, hey, routing table, tell me to get to that next hop IP, out which interface do I go? And it tells me directly connected fast Ethernet 00. So then we do a show IP, OSPF interfaced fast Ethernet 00. And what are we looking for? We're looking for the cost. So my cost on router 4 to get over to router 6 is going to be 1. So we're going to come back over here, and I asked router 4, I said, hey, what's it going to cost me to get over here? Our cost is 1. And we're getting ready to talk about auto cost reference bandwidth here in just a second. So the cost is 1. So that gets me over to router 6. So now that I'm on router 6, I'm going to say show IP route for 6.6.10.6. And it tells me that it's directly connected, right? So there is no next hop, because we're here. It is this loopback network, or this loopback address that we're trying to get to, is directly connected via loopback 10. So if I want to see the cost for router 6 to make it to that next hop via loopback 10, I would type in show IP OSPF interface loopback 10. And we are at the end of the road here, right? We have reached our destination to get to that network, and that cost is 1. So I come back up here to the drawing, and I've asked router 6, hey, what is your cost to get to these to get to those loopback addresses? And I did not want to do that. Let's do edit undo. So it moved it over. Yeah, so the pin has, give me a second here. So the pin has just hijacked my drawing. We may have to bring it back up. So let me do file, and we'll pull it back up here. All right. Even better. A little larger. So here we are, the same drawing, right? This button on the pin has been my demise in many videos. So I've asked router 6, I've asked the routing table on router 6, hey, what's the cost, right, or I should say the OSPF process, what's the cost to get from router 6 to your loopback address? And it's 1. The cost of that fast Ethernet interface is 1, and the serial link is 64. So 64 plus 1 is equal to 66. And so router 5, he believes, right, and he understands that my best path to get there, do show IP route, my best cost to get there is 66, and it's going to be out my serial 010 interface, because that's the only way he knows how to get there right now. So we're about to change that. And let's see, let me slide this over a little here. Drag this guy over a little here. All right, so let's see what happens on router 5 when we bring online that FA00 interface. So we're going to say no shut. We're going to put the IP address on there, 10.56.56.0, and its subnet mask is 255.255. Oops, apologize. I'm going to put in 56.5. There we go. All right. So we've got that added in. So do show IP OSPF neighbor. What do we see? We still only see router 4. So if I do a do show run and section OSPF, let's see if we actually configure that network. We have not. So let's add in, or I shouldn't say add in that network. We're going to turn on the OSPF process onto the FA00 interface on router 5. So router OSPF 5, and let's add in network 56.56.0, wildcard mask of 0.0.255, and it's going to be in area 0, right? So over on router 6, nothing's happening. If I do a do show IP interface brief, show IP interface brief, you can see that we have not configured fast Ethernet 00. So let's go ahead and do that. We'll go to global config mode. We're going to go into the interface configuration mode for fast Ethernet 00. We're going to do a no shut to bring the interface up. We're going to put an IP address on there, 10.56.56.6 with a /24. And now if I do a do show IP interface brief, you can see that the interface is now configured and it's in an up and up state. So let's do a do show run section OSPF to see what our OSPF section looks like. And we need to add the network statement here. So router OSPF, our process ID is 6. And again, you should see that we've set a process ID of 6 on router 6, 5 on router 5, and 4 on router 4. And OSPF is working beautifully. So to prove that that process ID, that is locally significant to the router, right? It has nothing to do with the adjacencies establishing. So network 10.56.56.0, and we're going to say all IP addresses that fall into that subnet mask range are going to be in area 0 on this router, and the OSPF process is going to run on that interface. And let's see if we see any messages here. We should see, and there it is, that we now have an adjacency established. But let's step back over to router 5. So he's also gone from loading to full, right? So if I do a do show IP OSPF neighbor, router 5 now has 2 neighbors. Again, the router ID is your neighbor ID. So router 5 sees router 6, and he sees them on a multi-access segment. And you know that because there's been a DR-BDR election that's taken place. He knows about router 4 on a point-to-point network type, and we know that because the priority is 0 and there has been no DR-BDR election. All right, but there should be a significant change here. If I do a do show IP route now, whereas before router 5 thought that the best route to get to 6.6.12.6 and 10.6 and 11.6 had a cost of 66, now he has figured out, and OSPF has informed him that, hold on a second, 66 is no longer the best cost to get to these networks. The best cost is 2. It's been inserted into the routing table, and it's going to be via the next hop address of 10.56.56.6. So as you can see, OSPF quickly recalculated the shortest path first, ran the Dijkstra's algorithm, and has determined that coming across this gig link with a cost of 1, I'm sorry, it's not a gig link, fast Ethernet link with a cost of 1 and then the cost of 1 to make the hop here to the loopback network or the loopback interface is 1. That's 2. And so that is much better, right? The cost is 1 here. It's 64 to go this way, right? But if router 5 just comes this way, the cost is 1. So the total is 2 to go this way. To come to router 4 and then to router 6 and then to the loopback, it's 66, right? So OSPF is very smart and has figured out, hey, 2 is much better than 66. And so this is the route that gets inserted into the routing table. Again, all things being equal, they're both OSPF, so the administrative distance is 110 for both routes, right? However, the route with the best cost is 2, and he is the one that will be inserted into the RIB, or the routing table here. All right, so let me clear the screen, and we'll come back here because now we want to take a look at something else. So over on router 6, let's see what router 6 has learned and what he knows about. So if I do a do show IP route on router 6, and there it is, excellent. So router 6 has learned about this network right here, and it's learned about it from OSPF. However, this is very different, right? Now we're seeing 2 routes to get to this remote network. And why is that? Because again, remember, the administrative distance of OSPF is 110. Our cost for both of these is 65, because it's going to be a cost of 1 and then a cost of 64. But that cost is going to be the same irrespective of whether we go, and let me change colors here real quick. Let's go, we'll change it to blue. So if I go this way to get to that network, if I come this way, it's going to be 1 plus 64, right? For a cost of 65. But if I go this way, the cost is also 1 plus 64 for a cost of 65. So we have a tie. We have 2 equal cost paths, right? So it's equal cost multipathing. So OSPF is also smart enough to know that if I have 2 equal cost paths, I can leverage both of those. So let's see if I do a trace over to 10.45.45. We'll say, which one do we want to use? 4. So I'm going to do a trace route over to that 10.45.45 network, specifically the 10.45.45.4. Let's see what router 6 chooses as the path for the first ICMP packet. So in this instance, it chose router 4. Let's see what it chooses for the next packet that it sends out. Aha! Now it sends it out to router 5. So the first packet goes to router 4, the second packet went over to router 5, and then the third packet goes to router 4. If I run this immediately again, does it pick up from where it left off? Which would be, is it going to continue to load balance across these equal cost paths? We should see 10.56.56.5. And we'll give it a second here. And there it is. And then what about the next packet? Where does the next packet go? The next packet goes to 10.46.46.4, and then the next packet should alternate back and forth. So traceroute is a great way to see that these the costs here, or I should say the paths that are being taken, they're alternating, right? Because we have equal cost paths. So both of those paths get inserted into the routing table, and we can load balance across them. All right. So now what we want to talk about now is, and let me come over here real quick and see how many of these I can go back. I think it's only 30. I'm not sure if it's going to get me to where I want to be. It did not. So I'm going to say File, Open Recent. We'll pull this back up. Okay. So there we go. Just wanted to clear that out real quick. Okay. So now what we're going to talk about is the auto cost reference bandwidth. Because you might be asking yourself, well, I think that's great that we know that the cost for the serial link is 64. We know the cost for the fast Ethernet link is 1. And we know that the cost to get to a loopback network from the router on which it's configured is also 1. But why is that? And so it all comes down to the auto cost reference bandwidth. So in OSPF, and specifically on iOS, and that's what we're talking about here, right? The Cisco Internet Network Operating System, the auto cost reference bandwidth, run out of room here, is by default, the value that's used is that for 100 megabit per second interface, right? And so what does that mean exactly? So 100 megabit per second interface has a cost of 1, and this is the reference point that we use to start all of our calculations on. And so when you're doing your calculations, you can break it down to bits per second or not. So let's take a look here. So on router 6, if I typed in auto cost reference bandwidth and question mark, you can see that the reference bandwidth is dealt with in terms of megabits per second when you go to configure it. So 100 megabits per second, I could do, if I wanted to talk about a gig link, that would be 1,000 megabits per second, right? And this is equal to a gigabit. If it's a 10 gig link, it would be 10,000 megabits per second, and that would be a 10 gigabit per second link. So the cost is 1 if this is being used as our reference point. However, what if it is a gigabit link, right? What is the cost of a gigabit link? Well, it turns out that the cost of a gig link would also be 1. A 10 gig link would also be 1. And let's say I had a 100 gig link, so 100,000 megabits per second, that would be 100 gigabits per second. That cost is also 1. Because here's how you calculate the cost. You want to take the reference bandwidth, and in our case, for the default, it's 100 megabits per second. You got to convert that. You need to convert that into bits per second, right? So 100 million bits per second is 100 megabits. So that would simply be 100 million, right? So 100 million is equal to 100 megabits per second. And this is our starting point, right? By default, that is the reference point from which we start when we're doing our calculations to figure out what the cost of a link is going to be. So if that is the default cost, and I want to figure out what is it going to be for a 1 gig link, right? So 1,000 megabits per second is going to be 1 billion 123 bits per second, right? So this is a gigabit per second. So I have to divide the reference point by the bandwidth of the interface to get the cost. So it's very straightforward. However, here, right, if my reference point is 100 million and I try to divide by a billion, I'm going to get a non-zero value, right? Or it's going to come back as 0. However, for costs, you can't have that. So that's why with an auto cost reference bandwidth, or the reference bandwidth is set to 100 meg, a 1 gig interface, it's going to be a non-zero number. It's going to be, or come back as 0 if you're doing integer division. You can't have 0 as the cost, so the cost would be 1. And that's the problem. As you continue to go up and use, like let's say we had 10 gig interfaces, right? So 10 billion, bits per second. it's going to come back as 1. And so this is one of the challenges with OSPF, is that it treats a 10 megabit per second interface the same as a gigabit or a 10 gigabit or a 100 gigabit interface. They're all treated equally and given a cost of 1, right? Now that's not what we would want. If you had 3 routers, right, and we'll take a look at what we're looking at right now, right, and this is router 6, and this is router 4, and this is router 5. Whoops. And let's say that these are all, this is going to be 100 gigabits per second, and this is 100 gigabits per second, and this is 100 megabits per second. Which way would I want my traffic to go, right? This is obviously the shortest path when you're talking about hop count, right? Because I've got 1 hop to make. However, look at the bandwidth here. It's only 100 megabits. This is 100 gigabits per second. The problem is that OSPF is going to say the cost to go this way is 1, the cost of that link is 1, and the cost of this link is 1. So this would be 2, and then obviously if we have our loop back, it's going to be 1. So the total cost would be 3 to go this way, but it would only be 2 to go this way. But is this way the smartest choice? Probably not, because we've got much more bandwidth over here, right? So we need a way to differentiate between the different link speeds. And that where we want to give preference, you know, so 100 meg, right, is okay. But if we've got a 1 gigabit per second link, we don't want that to be treated the same as the 100 meg. And the same thing goes for a 10 gigabit per second. We don't want a link that's 10 gigs to be treated the same as 100 meg. So how do we do that? So the way you do that is with the auto cost reference bandwidth, right? And so what we can do, and when you set this, it has to be set all throughout the area so that it's the same. That way you don't have calculations that are inaccurate. So the auto cost reference bandwidth is, where do I want my starting point in my network to be in terms of calculating the cost of the links? So if I only have 100 meg links and a serial link here, that doesn't say that, you know, sometime down the road that we're going to maybe add in, you know, router 7, and he could be connected up here, and these could be 10 gigabit per second here. It could be 1 gigabit per second here. I want a way to make sure that I not only build my OSPF area for scalability, but that I also build it to the point where I'm not going to have to come back in and change this auto cost reference bandwidth for quite some time, right? So the other thing is, with the auto cost reference bandwidth, you don't have to set it to the speed of your fastest link. I can actually set it to anything up to 4 terabits a second. Now, what we're going to see, and I'll show you this in a second, I've got a small shell script here that I'll share with you that will calculate the auto cost reference bandwidth, and it'll show you for different link speeds what it does to the cost. All right, so what we're going to do here is we're going to change the auto cost reference bandwidth. We're going to change it from its default of 100 megabits per second, because we know that someday we're going to have 10 gig interfaces, right? Or 10 gig links. And we're also going to have 1 gig links at some point. So let's change this from 100 megabits per second to a gigabit a second. And so that would be auto cost reference bandwidth. And again, when you make the setting here, it's done in megabits per second. When you do the calculation for the cost, you need to convert it to bits per second. So I'm going to set it here, and you'll notice, very nice, we get a message telling us that the auto cost reference bandwidth, it needs to be consistent across all routers in the area. So I'm going to go ahead and copy that. We're going to come over here to router 5. And again, I go from user exec to privilege exec to global config mode, and I do this is set under the OSPF process for the router. So we're going to set that cost to 1,000, which is a gigabit. I'm going to come over here, go from user exec to privilege exec into global config into router, configuration mode for OSPF, and we're going to paste that in. So on router 4, let me roll up here. Let me see if we had a show IP route. We didn't. Come over to router 6 before I run the show IP route. Okay, great. So as you can see here, router 6, right, he sees his cost as 65 to get over to this serial network, or this network link right here, the 104545 link. His cost was 65. So now that I've changed the auto cost reference bandwidth, it's no longer calculating the cost using as a baseline 100 meg interfaces. It's using gigabit interfaces as the baseline. So now let's see, do show IP route. Now what is my cost to get over there? Very different, right? So the cost is now 657, whereas before it was simply 65. So let's take a look. Let's see, why is it to get over there that it's 657 now? So from router 6's perspective, I'm going to do a do show IP route, and I'm going to ask it 10.45.45. Or not 45, I'm sorry, 10.56.56.5. What is my route to get over there? So it says that my route is the directly connected fast Ethernet interface. So I need to check and see what is the OSPF cost out that interface onto that link. So it's do show IP OSPF interface fast Ethernet 00. And as you can see, it's a broadcast network type, and my cost is now 10. So if you remember before, when we were using the auto cost reference bandwidth of 100 megabits a second, this had a cost of 1 because it was a fast Ethernet interface, right? Now we've changed the baseline and we've told OSPF, I don't want you to calculate things using 100 meg as the baseline anymore, right? This is no longer my reference point. It's not my baseline. My baseline is now 1,000 megabits per second, which is 1 gigabit per second, right? So what it's done is it's actually gone ahead and taken the reference bandwidth. It's no longer 100 million, it's now 1 billion, because this is a gigabit per second, and I'm now dividing the link speed by that number. So my link speed in bits per second, remember we're dealing with bits per second here, the link speed is 100 meg, right? So it's 100 million bits per second. However, my baseline and what I'm calculating my cost off of is not 100 million bits per second anymore. It's a gigabit per second, which is 1 billion bits per second. So when you do this division here, what do you end up with? You don't end up with 1 like we did when it was, the baseline was 100 meg. You end up with 10, right? And that is where the cost has now changed. So let me change my color here real quick. So now the cost is no longer 1 across this link. It's a fast Ethernet link, but the baseline for our calculation and determining the cost is 1 billion bits per second. So my cost now is 10. So we know it's 10. So now let's see what it's going to cost us to get from the router to this, from router 5 to that link. So we'll come now over to router 5. If I do a do show IP route, we should also see that the cost has also changed, right? Or has it? My cost still shows as 11. So let's do a do show IP OSPF on 10.45, oops, yeah, .45.5. Or I apologize, do show IP route 10.45.45.5. And you can see it's directly connected. So what is the OSPF cost out that interface? Do show IP OSPF interface serial 010. Aha. You can now see that the cost is no longer 64, it's actually 647. And so It's no longer 64 here, it's 647. So if the cost to go from here to here is 10, and then to get to this network segment is 647, my cost is 657. So does that line up with what we saw on router 6? And it does. It's 657, right? But the key thing to take away here is we've changed the auto cost reference bandwidth. Let's come back over here to router 5, because we saw something that was odd, right? 11. Should it still be 11 on router 5? And so this is actually interesting here, because router 5 is running 12.4 code. So you'll notice the 15 code, when I do the do show IP route, the 15 code auto-magically picked up and recalculated the cost. Let's see if that was the same over here on router 4, which is also running the 15 code. Aha, did router 4 pick up the cost? It did not, right? So these are the old costs that were originally in here, where my cost would be 1 across this fast Ethernet interface and then 1 here. So sometimes you have to do a do clear IP OSPF proc. So let's clear the process, and let's see if my calculation has changed. It has not. So let's come back over to router 5 and do a do show IP route. Router 5 still sees the old cost. So if I do a do clear IP OSPF proc, let's see what happens here on router 5. Because the process is going down. Or I apologize. Yeah, we had the cost was actually 2. So it actually did pick up the cost. So do show IP route. I was actually thinking that I'm going to get ready to do another change here and that it had already done it. So it did pick up the cost, right? Because the cost is now 10, and then the loopback cost is still 1. So we're good there. All right, so now let's see what happens when we change the cost for the auto cost reference bandwidth. We're going to change it from a gigabit, because I know that if I'm constructing my network, that at some point down the future, I'm going to make a big hop here. I'm going to set it to, it's currently 1 gig. I'm going to set it to 100 gigabits a second. And let's see what happens. So auto cost reference bandwidth, remember it's megabits per second. So there's 100 meg, there's 1 gig, 10 gig, 100 gig. All right, and we're going to go ahead and grab this, and we'll copy it over here onto router 6. And I'm also going to come over and put it on router 4. All right, so now the auto cost reference bandwidth has been changed. I'm saying that I want my baseline cost, because I have to be able to differentiate between links of different speeds. Specifically, if I'm paying to put 100 gig links into my environment, I don't want those to be treated the same as a 1 gig link. I want those to be different. I want them to be treated differently. So I'm going to manipulate the auto cost reference bandwidth, and I'm going to say my new baseline in my environment is now 100 gigabit per second. So let's see what that has done to our costs. So on router 4, you can see that it's now 1001 across a across 100 megabit per second interface. So the cost is 1,000 now, which we would expect, right? Because if it's 100 megabits per second here and I've changed it to 100 gigabits, the cost has now gone up to 1,000. Let's take a look on router 6, show IP route, and he's definitely going to see some different costs to get over to the interfaces on that serial network over there, or to the routes to get to the serial network right here between router 4 and 5. So now the cost is 65,766, right? And let's take a look at how do we calculate that. So if I do a do show IP route to get to 10.45.45, 46.46.5 5. Whoops, 45.45.5. Sorry about that. Okay. So how do I get to that network? You can see I've got 2 equal cost paths to get there. We're going to take this one here, and it's out fast Ethernet 00. So this is where I say do show IP OSPF interface fast Ethernet 00. What's the cost of that link? So the cost is 1,000, right? Because it's a 100 meg link, and the reference bandwidth, our baseline, is now being calculated off of 100 gigabits. And so real quickly, if that was 1 gigabit, 100 gigabits would be 100, comma, 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3, divided by the actual, so this is the actual speed of the interface. And so we're dealing with 100 meg interfaces, so my actual speed is 100 million bits per second, right? So when you do the math here, this breaks out to 1,000 because we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros. So if I take away 2, 3, 4, 5, 6, 7, 8 zeros, I'm left with 1,000. And so now the cost of this link is 1,000, right? So what's the cost of that link? Let's take a quick peek here. And now we know we're over on router 5. So I'm going to tell or ask router 5, I'm going to say, show me the route to get to 10.45.45.5. The router is going to tell me that's directly connected via the serial 010 interface. So now what's the cost of that link? Do show IP, OSPF interface serial 010. Right? So my cost is 64,766 now. So 64,766. So if I add 1,000 to that, what do we end up with? We end up with 65,766. And so that's how that's being calculated. Now, from a design perspective, right, and this may be a little beyond the CCNA, but I want to make sure that we talk about it. From a design perspective, you're probably asking yourself, well, wait a minute, if I set it to a gigabit a second and then my environment changes and I start to add 10 gig interfaces for some reason, then I've got to go back in and I've got to change the auto cost reference bandwidth. This is true. And then if I go from 10 gig to 100 gig, so why would I not just set it to 1 terabit per second, right? Which you can certainly do. We're going to do that right now, and let's see what happens. Specifically, keep your eyes on the cost of this network here that's on our serial link. So I'm going to go ahead and I'm going to do auto cost reference bandwidth, because I'm going to set it to a terabit because I don't want to have to touch this for the next 5 to 10 years, right? So we'll say auto cost reference bandwidth. Remember, it's megabits per second, so that's 100 meg, that's a gig, 10 gig, 100 gig, a terabit per second. So let's grab that statement, and we'll come over here and we're going to put it on router 5, and then we're going to put it on router 4. All right, so I've now just set the baseline. I've told OSPF that when you're calculating your cost, you are going to use 1 terabit per second as your baseline, right? So let's come back over here, and now let's do show IP route now, and let's see what the costs show. So the cost is 75,535, but it didn't actually jump that much, did it? Because before it was 64,000 or 65,766. So it didn't jump that much. So let's see what the link cost is now from router 6 over to router 5. So if I do a do show IP route, tell me how to get to 10.45.45.4. So again, it's out that fast Ethernet interface. So I do a do show IP route. I'm sorry, do show IP OSPF interface fast Ethernet 00. And my cost now is 10,000, right? Which we would expect. So the cost for this link is going to be 10,000. So now I jump over to router 5 and I say, show me how to get to 10.45.45.5. How are you getting there? I'm getting there on the directly connected interface, serial 010. So to see the cost of that link, it's show IP OSPF interface, serial 010. And you'll notice that the cost is $65,535. Now, it's interesting because prior to this, it was $64,766. So it didn't actually go up beyond $65,535. So we just set the auto cost reference bandwidth to a terabit a second. What if I set it to 10 terabits a second? I can't, right? The value is too large. So at a terabit a second, we get 65,535. What if I set it to 4 terabits a second? So that's 400 meg. That's 4 gig, 40 gig, 400 gig, 4 terabits a second. Let's see what happens here. We'll drop this back in, and we'll drop it back in over here. OSPF is going to do its calculation. So now if I do a do show IP route, let's see. All right, the total cost of the route has grown, right? We would expect it's going to recalculate the cost of this link here, as well as the cost of the next hop, which in our case is at serial 010. However, we have maxed out the cost. So this is the sort of inverse problem that you could run into. The inverse problem is that we set the reference bandwidth, we set our baseline so high, which we just did. We set it to 4 terabits a second, right? So we set it to 4 terabits a second. However, now our serial link, right, which is obviously much slower, okay, it's only 1.544 megabits per second, or 1,544 is what you'll see on the interface when it's set on the interface. So it's only 1.544 megabits per second, right? The maximum cost that we can have is $65,535. So now what's happening, we've got the inverse problem, where before, when we had our reference bandwidth at 100 megasecond, we had, and we'll take a look here, let me jump over to the notepad here, and this is very important, right? So before, when the auto cost reference bandwidth, right, when our baseline was 100 megabits per second, all right, this was great 5, 10, 15 years ago. This was okay to have because you didn't have a lot of interfaces faster than this. Today we do. So initially 1 meg or 100 meg, 1 gig, 10 gigabits per second, 100 gigabits per second, they were all treated the same. They were all treated with a value of 1. So now with interfaces that are much quicker than this, we want a different baseline. So in my case here, I push the baseline up to 4 terabits per second, because what I'm saying is I don't want to have to come in and adjust this again for quite some time. I'm just going to max it out. We're going to say 4 terabits a second. So again, the inverse problem is now if I've got a 64K link, kilobits per second, right? Maybe a fractional T1 or 128 kilobits per second, or 256 kilobits per second, or 512 kilobits per second, right? Which would be, that's what you might see on this link here, right? A serial link. Now that I've got 4 terabits per second as the, whoops, I'm going to escape out of that real quick. Now that I have 4 terabits a second as my baseline, right? These slower links now have the same problem the faster links did when the reference bandwidth was low. Because now all of these guys, they've maxed out at 65,535. So the problem here is now just the opposite, where a 512K link is going to be treated the same as a 64K link. And so you need to make sure that you're very careful when you're setting your speeds. And so real quickly, I have a shell script here that I worked up this morning. And again, definitely not to be judged on brevity or best practice or security, things like that. But if I do a more on autocost reference or autocost OSPF bash, so here's the script. You would want to, if you wanted to recreate this, you would want to pause here. Obviously, you can't cut and paste. Unfortunately, you're going to have to retype it. But it's not too long. And let me go down to the bottom. And so then there's the bottom of the script. So I'm going to run the script now. And what this script does is it's going to go ahead and it's going to take, it's going to prompt you. It's going to say, so enter the desired OSPF cost, reference bandwidth in gigabits per second. Because again, the original reference bandwidth is 100 meg. So my next step up is going to be a gig. So we'll enter the value in gigabits per second. So I would say I want to use autocost reference bandwidth of 1 gigabit per second. I hit enter and my script will actually tell me for these interface speeds here, right? So we have 64K, 128K, 256K, 512, a full T1, 1.544, and then it goes to 10 meg, 100 meg, a gig, 10 gig, 100 gig, and a terabit a second. It's going to tell you what the cost would be for links of those speeds. So at 1 gig, you can see our problem here at 1 gig is still that 1 gig, 10 gig, 100 gig, and a terabit, they're all treated the same. So if I wanted to see what is it going to look like for 10 gig, that's what my values would look like. And you can see as soon as you change your autocost reference bandwidth to 10 gig, a 64K link and a 128K link are identical, right? That their values max out at 65,535. So where does that happen? Let's check at 100 gig. Wow, at 100 gig, take a look here. Right, at 100 gig, a 512K link, a 256K link, a 128K link, and a 64K link, those are all going to be treated the same. All right, and then our last one was a terabit per second. You can see that links from 64K all the way to 10 megabits per second, they are now going to be treated the same. Right, the cost, I should say, is going to be the same. Cost of 100 meg is now 10,000, but at a terabit, if you've got nothing but 100 meg and higher, or I should say 100 megabit per second and faster interface speeds in your environment, then a terabit's not that bad of a thing, right? And so real quickly, one final tweak that you can make to the script, if you ever have to work with Nexus, Nexus uses a reference bandwidth of 40 gigabits per second, I believe. I'm pretty sure that's the Nexus side of the house. So let's say that, and you could have, there 40 gig interfaces are also available today. So if I wanted to VI this script, and I'm going to come down here, and these are my link speeds. There's 10 meg, there's 100 meg, 1 gig, 100 gig. So I'm basically going to do 40 gigs, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I would say 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've just added that into the script, right? And I'll show the script one more time so that you could pause if you wanted to see what it looked like. So now when I run it, I'm going to take into account 40 gig interfaces. So if I said a 40 gig interface, if that's what I set the autocost reference bandwidth to, here are what my values would look like. What if, again, let's set it to 100 gig. So an autocost reference bandwidth of 100 gig, here are my costs. And so this shows you the cost of a 40 gig link is 2, a 100 gig link is 1, and a 10 gig link is 10, because obviously the 40 gig link is faster than the 10 gig link. So here are the costs. So again, let me go ahead and I'll do the more command on that script. And again, I just quickly whip this up. So you enter, you clear the screen, prompt the user for input. You're going to check to see, right, is my autocost reference bandwidth, is what this individual is entering in, is it greater than the maximum that's allowed? You need to make sure that it's not greater than the maximum allowed. I clear my screen. Again, I convert whatever got entered in, I convert that into bits per second, and then I simply loop through these different link speeds, and it goes around to make sure that it wraps here, right? So I just loop through the link speeds, and then I print out what the auto cost reference, or what the cost would be for those link speeds. And again, if it's greater than 65,535, we know that that's the max, so then I just leave it at 65,535. So, and you can see I'm on router 4 here. If I were to type in, let's go into a specific interface, we're going to do this in a second, interface fast Ethernet 00, IP OSPF cost, the maximum cost I can put on that link is 65,535. And so that's why it caps out when we're tweaking that auto cost reference bandwidth. All right, so let's go ahead. We're going to take off the auto cost reference bandwidth. We're going to go back to our default value. So I'm going to say, where is it at there? I think we just set it to, did we set it to 40? Let me see what it is here. Hold on a second. So do show run section OSPF. And it is, well, actually, I just typed in the command. So we're going to do Control A. We're going to say no auto cost reference bandwidth, and let me make sure that that's gone. All right. So we're going to pull this off. So do show run section OSPF. All right. So it's set there again like that. So we're going to say, I'm going to copy that. I'm going to say no and paste that in. And then let me grab that command. I'm pretty sure that's what we set on 6. And comp T router OSPF 6. And we'll paste that in. All right, so now it's been all the auto cost reference bandwidth. We've gone back to the default, which is 100 megs per second or 100 million bits per second. So now if I do a do show IP route, whoops, our costs have come down, and they're much easier to look at right now, right? Okay. So the next thing that we want to talk about is what we just kind of alluded to, was instead of tweaking the OSPF reference bandwidth, the other way that you can manually change the cost of a link is to simply go on to the interface on that link. So on router 6, it would be interface fast Ethernet 00. And I can put a cost in here. So I can say IP OSPF cost, and I'll do a question mark here. Again, you can see that the speeds that we can choose from, or I'm sorry, the costs that we can choose from range from 1 to 65,535. And so it's at this point where we would want to make a determination, what do we want to set the cost of this interface to? So I could go ahead and set it, let's go ahead and set it to 65,535, right? Now, very important, I'm going to go ahead and set this, I'm going to copy this here. If I do a do show IP route now, right, what happened? To get to this 1045/45 network, I no longer have two equal cost paths, right? I have a single path to get there, and it's telling me to go this way to router 4 and then here because the cost is 65. Now, there is another route to get there, right? It's going this way from 6 over to 5 and then to get to that network, but we've just changed the cost. That route is not going to be inserted into the routing table. So if I were to shut down FA01, so I'm going to take away this path. Let's see what happens. So my OSPF adjacency with that neighbor is down. However, when I do the show IP route now, was OSPF smart enough? Yes, it was. And as you can see, it took into account my cost that I added on the interface to get there. However, if I come over here to router 4 now, right? So router 4 no longer can go this way. He no longer has a path that way. If I take a look from router 4's perspective and do a do show IP route and ask him, hey, how do I get to 6.6.10.6? It's going to tell me to go to router 5. So let's see what the cost to get there is right now. So it's telling me the cost to get there is 66. And this is very important, right? Remember, and I'm going to go ahead, let's open up, I'm going to open it up again here. So remember, we changed the cost on that interface right there with the IP OSPF cost command. And we set it to 65535. So on this router, when I looked and said, hey, to get over to that network, what's my cost? It took this into account. We shut this interface down, and on router 4, I'm asking router 4, hey, how do I get over to these networks here, or at least to the 6610? It's telling me to go this way, but it's not adding in a cost of 65535. We can clearly see it's telling me the cost is 66, so we know that by default, that serial link will be 64. That's going to be 1, and that's going to be 1. So what happened here? I only set the cost on one side of the link, which means that router 4's view, right, and let's take a look and see what router 5 thinks, that they're not taking that into account. Oh, whoops, I'm sorry, do show IP route. Show IP route. Just want to see the cost. Does router 5, no, and again, so you can see here, router 5, he does not care either, right? So router 5 still sees the cost to get there is 2, which is correct because it's going to be 1 here and 1 here. So if we truly want to manipulate the cost of this link and not just the cost of, or router 6's view of this link, I want to change the cost of this link in both directions. When you do this, make sure that you set that on both sides of the link. So on router 5, I would come into interface FA00 and I would say IP OSPF cost, and we're going to set it to 65535. Now, actually let me clear that out. Now if I come back over here to router 4, you can see before router 4 just thought it was 66, but if I do a do show IP route now, you can see that, aha, now the cost to get there has been changed. And so that's truly what we wanted to do. So remember, when you set manually the IP OSPF cost, you want to set it on both sides of the link. Okay, so then we're going to take a look at one last thing, and I'm going to go ahead and do a no on that. Whoops, sorry, I was on router 5 and 6. So I'll say no IP OSPF cost. And this is, again, you can do this instead of having to set the auto cost reference bandwidth throughout your environment. This is the alternative. So if you did have a bunch of links that were much slower and the auto cost reference bandwidth was maybe at 1 gig and you didn't want to go to 10 gig because you're going to run into the issue where slower links would then be treated, that would not be differentiated, they'd be treated the same, the inverse problem that we have, you could come in and use the IP OSPF cost command. So I'm going to turn that off on that interface. Let's go over here to router 6. Oops, I'm sorry. Where did I set that? Yeah, on router 6, and we're going to turn it off there. So now if I do a show IP route, you can see that we still have the old costs in there. And did I actually set that on the right interface? I did not. Let's check it out, interface 00. Let's make sure that well, actually, let's do a do show run int FA00. Let's see if yeah, I left it on there by mistake. So let's take it off of there, show IP route now, and what you're going to see is we've still got the same cost. Let me make sure, do show run int FA00, where I set that, it's not there. Make sure I didn't make a mistake here. Do show IP OS, oh, I'm sorry, do show run int FA00. Did I get the wrong interface? No, it's off of this interface, so do show IP route. All right, so he sees the right costs again. Let's check it out here, do show IP route. All right, he sees the right costs again, and let's come back. Oh, we've got that link shut down. Let me bring, and did I shut it down on 6? Do show IP interface brief. All right, so those guys are up. So I think it's on 6. Do show IP interface brief, where we tweak that interface, yes, administratively down. So fast Ethernet 01, no shut. Because what I want to see is I want to see my equal cost paths from router 6's perspective. I want to make sure that I see both paths. Do show IP route over to the 1045.45 network. So he doesn't see them. He sees the one still out to router 5, and I'm trying to make sure I did not tweak anything else. So let's do clear IP OSPF proc on router 6, and do show IP route. All right, so I must have something lingering out there. Let's do clear IP OSPF proc. Do show IP route. All right, so it's still, all right, still doing its calculations, so there we go. Now let's do one last one here on router 4. Do clear IP OSPF proc. We'll say yes. Let me come back over here to router 6. Do show IP route. And he still sees only the one path out fast Ethernet 01. So I've changed something, and for whatever reason I've changed something. And do show run int FA00. It's not there. FA01. Let's make sure I did not change anything. And on 05, do show run int FA00, and on serial 010. All right, and let's check router 4. Do show run int FA00. Okay, everything looks good there, and do show run int serial 010. All right, everything looks good there. So for whatever reason, do show IP route. Router 6, aha, impatience, I guess. So router 6 finally ran the SPF calculation. I've got my equal cost paths back, and that's what I wanted. I was just simply not patient enough, I guess. All right, so we've got that. The final thing we're going to look at, so we've looked at the auto cost reference bandwidth. We've looked at the IP OSPF cost and setting that manually. And remember, it needs to be set on both sides of the link. And we're going to look at one last way to tweak the cost calculation. And that's going to be by, and I'm on router 6, so let's do a show run int on, or show int on FA00. We'll tweak this link between 6 and 5 one last time. Oops, do show int FA00. Okay, and so it's the bandwidth statement. And so you can see right here, and where iOS is getting this, right? The iOS is getting this based off the type of interface that is inside the router, right? So this interface is a fast Ethernet interface, so by default, the bandwidth in kilobits per second is going to be 100,000 kilobits per second. If I hop onto router 5 and we run that command, do show interface serial 010, you can see that the bandwidth for a serial interface by default, because it's an actual WIC, a WAN interface card that's inserted inside this 1841 router, that is router 5, a serial interface is 1,544 kilobits per second. Now, we're going to change this. So this is another way to change how OSPF does its calculations. The important thing to remember here, though, is that when I make the change to the interface, right? So I'm in interface fast Ethernet 00. If I say, whoops, bandwidth on router 6, if I change the bandwidth here to 1544 and I hit enter, the key thing to remember is what I just did right there does not change the actual bandwidth of that interface. By making this change, by that statement right there, all I've done is I have told OSPF and EIGRP, as well as quality of service, QoS, all I've done is I've told those protocols and those features to treat the speed of this interface as if it's a serial interface. I'm still going to be able to pass up to, and theoretically, 100 megabits per second. I'm just telling the routing protocols, right, EIGRP or OSPF in our case here, I'm telling OSPF, hey, treat that interface as if it's a serial interface. That's how I want you to calculate it. So again, we've seen 3 different ways to manipulate the cost of a link. Now, just like the IP OSPF cost command, I need to come over here to router 5, and I need to set it on router 5's interface fast Ethernet 00 as well. It has to be on both sides. So that IP OSPF cost, if I use that, got to be on both sides. Auto cost reference bandwidth has to be on every router in your OSPF area. And finally, the bandwidth statement here has to be on both sides. So let's go ahead and set the bandwidth statement here, and we'll do the same thing. We're going to set it to be, instead of 100 megabits per second, we're telling OSPF, when you calculate the cost of this link, which is this link right here, right? This link right here that runs between 5 and 6, you're going to treat that and do your calculation on that as if it's a serial interface. So now let me hop back over here to router 6. And did we have it? We did. So we had a show IP route after everything was cleaned up, and you can see what's our cost. It's 65, right? Because remember, the cost of this link was 1 because it was a 100 meg interface, and our baseline, our auto cost reference bandwidth by default was 100 megabits per second. So it's 1. When you divide those two, you get 1. Now we've made the change here and we've said, no, we want you to treat this link now, OSPF. When you do your calculations, calculate that as if that link is a serial interface. And now you'll notice it doesn't show up here. And why is that? Because from router 6's perspective, remember, he had 2 ways to get to this network, the 10.45.45.0 network. The best way to get there is 65, the best cost, and so it's coming this way, right? Because we've now tweaked the cost of this. This is going to be 64, or it should be 64. We're going to see. So, and then 64 and 64 would be 128. So how can I check? Well, let's go ahead. Let's go into interface FA01. Let's shut this interface down. And now let's see what happens. So by shutting down this interface again, right? So I shut this interface down right here. Router 6, he's only got 1 way to get to this network, and that's going to be via router 5. And so now let's see if we've got a cost of 128. And I'm just guessing there. Educated guess, we'll see. No. So router 6 still sees his only path to get to that network as going out, still sees the cost, the bandwidth cost as 1, right? And so he is making the next hop. He is going, that interface is down, so he's coming to router 5. However, we've made those changes. Those changes didn't take. Why did those changes not take? So if I do a do show IP route, and I say, how do I get to 10.45.45.5? It's out fast Ethernet 00. So then I do the do show IP OSPF interface fast Ethernet 00. My cost is 1, but we changed the bandwidth. The thing that's happened here is we've changed the bandwidth, right? But OSPF had already calculated the cost of that link. So do we need to clear IP OSPF proc, or the process for OSPF? I'm going to say yes on router 6, and I'm also going to come over here. Well, let's see. I changed it on router 6. Do we have anything different now? We don't. Let me come over here and change it on router 5. Do show IP, whoops, IP OSP, I'm sorry, we're going to clear the process. Do clear IP OSPF proc. So we'll say yes. The process is going to reset. Do show IP route. All right, so as you can see, we don't have any OSPF routes right now. All right, we've asked it to recalculate, and sure enough, and it might have been previous to this that I just wasn't being patient enough, but that's okay. Wanted to make sure that we got to see this value. So by forcing the process to restart on 5 and 6, so now what is our cost to get there? The cost is now 128. All right. So I am going to go ahead. We're going to stop this right here. I've actually been going for a little while. So we're going to go ahead and stop the supplement right here. This is basically all of Chapter 8 that we've looked at, right? Didn't do anything for V6, but the concepts are still the same, right? Because we're talking about the OSPF cost. So what did we do? We set OSPF up from scratch. We took a look at the debugs for OSPF. We took a look at the debug IP OSPF adjacency, the hello packets. We saw what happens with the router ID, how the router ID gets selected. We looked at the DR-BDR election. We saw why there are no DR-BDR elections on point-to-point interfaces. You now know how to check. How do I see if it's a point-to-point interface? How do I see if it's a broadcast interface? And then most importantly, and like I said, what becomes very confusing for a lot of new students is, okay, I understand how the cost is calculated, right? It's 100 megabits per second is my baseline, and then I take the interface speeds and divide that by 100 million bits, 100 million, which is 100 megabits in bits per second, and that's how I end up with my cost, right? We saw how you walk along each link in the cost to calculate the total cost to go from one side to the other. But most importantly, we saw how you right-size your environment. If you don't have serial links in your environment and everything is 100 meg and faster, then maybe you want to change that auto cost reference bandwidth to take advantage of those links in your environment that are much faster. Because you saw the diminishing returns, right? If you leave your auto cost reference bandwidth at 100, yet you've got 100 gig interfaces in your environment, what you're basically saying is you're saying that my 100 meg interfaces are going to be treated the same as my 100 gig interfaces. We also looked at the inverse of that, which is we decide we're going to go crazy and we're going to set it to a terabit a second as our baseline for our auto cost reference bandwidth. We saw what happens in an environment where, hey, I still have some legacy interfaces around. I've got some 64 kilobit per second interfaces or some 128 or 512 or 1.544s. My recommendation there was you probably should seriously look at an upgrade. But again, we saw what happens if you decide to go crazy and set it to a terabit a second and you don't have all fast links throughout your environment. Then we looked at the alternative to the auto cost reference bandwidth. What if I want to pick off selected links? There's two ways we can do that. We can do it with the IP OSPF cost statement. It's got to be on both sides. Or you can use the bandwidth statement. The difference between those two ways, right? The difference between those two approaches is the IP OSPF cost statement. OSPF doesn't have to do a calculation because you're telling it, hey, this is the cost of the link. Conversely, with the bandwidth statement on the interface at the interface level, for that, what's going to happen there is OSPF is going to have to do the calculation. As you saw over here, I wasn't patient enough and I forced a reset of the process because I wanted it to force OSPF to recalculate that cost based off the new bandwidth statement. But remember, even if you tweak that bandwidth statement, you are not changing the actual physical characteristics of the interface. So, and the reason that bandwidth statement is in use is if you have a fractional T1 here, right? And this is, I'll close with this. So this is a serial link. Let's say this, is your service provider and this is you, okay? If it's a T1, whoops, lost my thing there. Let me bring back the, I've got to get rid of this button on this, on this pen. So if that's a fractional T1, right, and it's 64 kilobits per second, right, or it's 128 kilobits per second, you want to use the bandwidth command here to actually force OSPF so that when it does its calculations, you want to force OSPF to calculate that interface correctly, the cost for this link correctly. Because again, if it's 64 kilobits per second and I don't use the bandwidth command, what's the default? The default is 1544, and that is what OSPF is going to use. We saw that over here, right? When we took a look at, and I'm on router 4, we didn't actually change anything on router 4. We saw that here on router when you did the show int, and there it is right there. So by default, iOS, when it boots up, it looks at the interfaces and says, oh, it's a fast Ethernet interface. It's 100,000 kilobits per second. Oh, it's a serial interface. It's 1,544 kilobits per second. In reality, though, if that is not the case, and this is a fractional serial link, fractional T1 or whatever, you want to use that bandwidth command so that it gets calculated properly, right? One command that we didn't look at is the clock rate. And the clock rate, that is definitely, that command will change the physical characteristics of the interface, right? And this goes into 257 where you start to talk about, you know, the serial links and the DTE and the DCE. But just remember that when you use the bandwidth command on the interface, and that's why I showed you here on the 100 meg interface, yeah, OSPF is going to change its calculation because we've tweaked what we want OSPF to think this interface speed is, but the speed of that interface does not change. We're not changing the physical characteristics with the bandwidth command. All right, so this has been a pretty lengthy video, and I really hope that you get a lot out of this. This is actually almost a mirror of my lecture for OSPF on Saturday. So if you didn't feel like you captured everything or that you understood everything, hopefully this has cleared it up. And again, you've got a shell script here that if you wanted to recreate, you certainly could. Again, not the best or the quickest way to do it. I just threw it together as fast as I could so that you could say, hey, if I set my auto cost reference bandwidth to 100 gigabits a second, what will the cost of these links here be? And you can modify the script if you wanted to change it to check for, 3200 or 32K or for a 2400 baud or whatever, right? So hopefully you've got a much deeper understanding of these technologies, and hopefully this has cleared up OSPF for you, single area OSPF, and I will see you all next week.